Building with a standard API means you own the tool execution loop. Think of it like this: rapidly spinning mechanical gear system. You call the model, you catch a tool request, you execute it locally, and you manually feed the results back to keep the gears turning. You write every iteration of that loop. Managed agents alter that architecture. That execution loop no longer runs on your hardware. It is moved to Anthropic servers operating inside their harness. When the server absorbs the process, you drop the burden of writing your own tool calling logic. But removing the local loop creates a distinct problem. A loop you do not control is a loop you cannot see. You lose direct observability. Surrendering that execution to a remote server dictates that you must learn an entirely new mechanism to monitor its progress and dictate its actions. The friction point in migrating to this architecture happens almost immediately. Developers deploy an agent, initiate a task, and then watch the application silently hang. The immediate deduction is usually hardware or network failure. Developers assume the API broke, the server crashed, or the model encountered an error. The architectural reality is simpler. The agent has not crashed. It is sitting idle, waiting for a response your code never sends. Treat the bidirectional event stream as the absolute control surface of the system. The server narrates its loop to you as a continuous stream of events, and it accepts your input precisely the same way. Decoding this exact stream is the only way to resolve the silent hang and achieve precise programmatic steering of your agent. Attaching an event listener correctly requires a strict order of operations. The most common initialization error is a race condition. This occurs when you send a user message payload to start the work, before the event stream is fully open to receive the response. Because the stream only delivers events emitted after you open it, a fast-acting agent will begin working and emitting data before your listener exists to catch it. You lose the critical initial events of the run. Looking at these execution timelines, the fix is the documented architectural pattern. Open the listener stream first, wait for connection, then send the payload. The official SDK natively enforces this. Inside its standard scope, you guarantee capturing every packet. Establishing proper initialization is the first step toward preventing silent failures at startup. Once the stream is open, we can map the exact data structures flowing across it. Communication here is bidirectional. This flow diagram maps that entire surface. On the input side, the control vocabulary is restricted. You are limited to exactly 5 user event types. For most operations, you will exclusively use the user.message event to initiate the task. Returning from the server, the output stream is much richer. These incoming packets divide into 3 distinct families. The first family consists of agent events. These narrate the actual work logic as it happens, including the text of its reasoning and the specific tools it invokes. The second family contains session events. These dictate the system status and handle the high-level control flow of the entire operation. The third family provides span events. These act as observability markers, wrapping the activity for timing metrics and token counting. 5 user inputs and 3 output families. That taxonomy forms the complete programmatic vocabulary of the agent. Now we can isolate the line of code that causes the silent hang we identified earlier. Look at this typical event loop. The instinct here is simple. When the loop receives a session.statusIdle event, it terminates the connection. But idle simply means I am not actively working right now. It does not necessarily mean the task is completed. To know whether the agent is finished, you must read a specific data field within the event payload called stop reason. The agent stops for one of 2 reasons. The first is a successful completion, requires action. It means the agent is blocked. It has hit a client-side dependency or permission gate, and it expands downward to reveal a nested array of event IDs. Those nested IDs identify the tool calls the agent is trying to make. It needs your application to approve them. If your client abruptly disconnects without resolving those IDs, the server-side process sits in an indefinite deadlock. The correct architectural pattern dictates that your client's event loop must internally branch. Upon receiving an idle status, it must check the stop reason and route the logic accordingly. An agent hanging is an agent trapped at requires action by a client application that failed to check the reason it paused. Because the stream is bidirectional, you have the capability to steer the agent in real time while it works. In a request-response model, an agent executing a long task down the wrong path is like a train barreling down the wrong track. You would have to sit back and wait for it to finish failing before you could issue a correction. The event stream removes that limitation. You can send a user interrupt packet to halt execution mid-process. This sequence diagram plots the interception. By batching a user.interrupt packet with a new user.message, you redirect the server-side loop to a new task in a single call. The agent stops, acknowledges the new direction, and proceeds. You achieve dynamic redirection without tearing down the session context, preserving system efficiency. We can now assemble a robust event loop based on these precise structural deductions. First, the application attaches the event listener before transmitting the initial payload, eliminating the race condition. Second, the connection loop enforces branching logic on every idle event to verify the status of the stop reason payload. This sequential code block builds the complete architecture. Attach the listener, send the message, loop the incoming events, branch on idle, check the reason, and add a session.error handler to isolate transient network drops from hard API failures. Adhering strictly to this pattern removes the ambiguity that leads to silent hangs. Moving from the raw data loop to the application layer shows the practical result of this design. This split-screen layout shows the direct translation. Parsing those specific JSON events directly powers a complex user interface. You control the output layer. Granular data packets, like the agent's internal reasoning, can be rendered for an engineering debug view or hidden for a polished production client. Once you establish this connection layer, future implementations, like custom tools and multi-agent delegation, all flow cleanly over this exact same stream structure. Mastering the stop reason hinge moves you past troubleshooting basic errors. It gives you the mechanical foundation required to orchestrate reliable AI architectures.